epilepsy children.
Yes, thank you for a nice introduction. It's my great pleasure to make this presentation. So this talk will briefly report our preliminary data, which suggests deep learning-based DWI Connectome analysis may be very useful to improve our detection of external alterations in language network of pediatric epilepsy by objectively and efficiently cleaning up messy and noise connector matrix in clinically acquired DWI data. So basically, this work will translate a deep learning technique to generalize and standardize the low quality of DWI data. So where low angular resolution is typically applied at low B values to image orientation of multiple fiber in order to save the scanning time. So I believe such approach will be very useful to standardize quality control in clinical DWI data. Oops. How do I move it? I did. Oh, yes. So as many of you already know, continuous ictal spiking disrupts language development, which leads to high instant rate of language impairment, up to 21% in pediatric epilepsy. For last decade, there have been a series of studies to image such impairment using DWI Connectome matrix SOV-IJ, where each element consists of a total number of streamlined connections between every pair of brain regions. However, this matrix inherently contains messy and noisy wiggly tract outliers, which limits its reproducibility across subjects and compound statistical inference in group comparison and functional correlate analysis. One reason we have such outliers is that current tractography method provides more false positive than true positive, as shown in this example, to visualize one branch of language pathway connecting the precentral gyrus to spatiotemporal gyrus. We believe that such outliers are mainly caused by intravoxel crossing fiber problem in clinically acquired data, where, as I said, we applied low angular the encoding scheme to detect the fiber orientation here. And also other experimental setups and parameters that may decide the degree of freedom to have such outliers. So unfortunately, there is no simple and basic rule of thumb to control such outliers in clinical situations. To include only true positive fibers in clinical DWI Connectome matrix, we set up this one simple and basic principle, stating that in the same temporal space, spatial coordinate of true positive fiber from clinical DWI data should be identical to those of true positive fiber from high quality DWI data, such as Hardy data in human connectome project. So under this principle, the inclusion of only true positives become the classification of a whole tractography into well-defined set of reference classes, so which consists of true positive fibers at group levels. So to solve this classification, we introduced deep learning techniques. So more specifically in our deep learning-based connectome analysis, we first construct the deep learning network to which deeply learn spatial coordinate of true positive reference fibers in template space. And then we spatially normalize any given fiber, either from the single shell or multi-shell to the template space, and classify its spatial coordinate into one of our reference classes of interest, so that we can reconstruct the DWI Connectome matrix SOV-IJ from the classified fibers, which do not include dirty false positive outliers. So idea is very simple. We wanted to make our window as clean as possible to look at very detailed and subtle change in connectivity metrics. The feasibility of this classification method was already demonstrated in our recent study, which published in IEEE TMI in this February. This work just proposed deep convolution neural networks, so DCNN, which deeply learns spatial coordinate of 64 functionally important white matter pathway classes. So whenever I talk about the class, that it means the neuronal pathway or piecewise connection in connectivity matrix. Okay. So as shown in this picture, basically we define the 64 white matter classes by combining the functional connectivity, the MRI, so with the DWI tractography, so that we can visualize the different type of primary motor pathway, or language pathway, or auditory and visual. So as shown in this picture, this network, the classified spatial coordinate of input fiber into one of 64 target classes. So this table summarizes the accuracy of this classifier. So compared with the conventional method, this network achieves very high correct classification, up to 95% in test set. Okay? So more technical details and procedure in this work is well described in this paper. In this work, we increased the number of target classes up to 1,477 to construct the DWI connectivity matrix, defining a backbone brain network in HCP template space. So basically, each class consists of two positive fibers connecting every pair of AAL ROIs, which were sorted out from the whole brain tractographies generated from group fiber orientation distribution function in template space. So basically, our DCNN network was trained to 3D coordinate of 100 equidistant fiber segments into one of our target classes. So network is just learn the nonlinear relationship between our input matrix, which is a 3 by 100. 3 means that we have the X, Y, Z, the coordinates. Then 100 means that we just equally the sample or given fiber with the equal distance. So our input size is 3 by 100. Then we already know the true class membership. So we use those two information to learn the network layers in this system. So I have to say this, why we choose this number of total classes and why we pick the 3 by 100 input size. It is because there's no hardware limitation. So our workstation in lab only handle such amount of data. So we just sort out the number of the fiber connection in our matrix. Then we just pick top 1,477. Then we just look at which sample numbers would be handled by in our LAMP size. Then we choose the 100. So this is the number we can try with the updated system. So anyway, that is why I call this matrix, it just define backbone network. So which define the major connections exist in our data. Okay, once training our network, the softmax layer estimate the prediction probability of a given fiber belonging to our reference classes. The final class membership was determined by selecting the maximum argument of prediction probabilities. So where we introduced our experimental parameter beta. Beta works as a threshold of prediction probability to take the fibers having high confidence level on the classification. So as shown in this example, which shows histogram of prediction probability in specific class C1159, which is the class, the neuronal pathway connecting left precentral gyrus to left thalamus. So if you pick betters in very low numbers, that means that we consider much denser the fibers in such class. So if you move beta to higher number, that means that we just pick very sparse the fiber in true positive fibers in that class. So this is experimental variable, so we need to optimize in control data. So we utilize single cell data of DWI in health control with 3 different p-values. Then we found that beta of 0.8 provide the highest inter-subject reproducibilities at all 3 p-values, as shown in this picture. Which means that if you set these parameters equal to the 0.8, we may ensure the best reproducibilities across the subjects. So that's the primary assumptions in this work. So indeed, we improve 20% of the intra-class correlation by setting beta at the 0.8 here. Okay, so this is the input to our DCNN. This is the output from our DCNN. So bottom move is shows the post-positive fiber excluded by the proposed method. It's very clear. So these post-positive fibers include short and long, the wiggly tract fiber, which we assume that this is the outliers, which you don't need for our analysis. So this slide demonstrates how DCNN can improve the reproducibilities in health control. So as marked by the white arrow, so this is the post-positive outlier. If we don't use the DCNN, we have this sort of the fiber track in this class. See, the probability value of this outlier is very close to 0.01 or 2, which means that by adjusting beta value, we can get rid of this one very easily. So it makes more homogeneous the inter-subject variations in connectivity matrix, as marked by the white the boxes here. This table shows that 0.02 over ICCA can be achieved by applying the beta equal 0.8. So here's the epilepsy data. We scanned 27 patients, epilepsy patient, and 17 the age-matched health control. So all subjects has language dominant in left spares. Each patient and each subject underwent the 3T single-cell DWI with this parameter. So we used MR3X probabilistic tractography. Then this tractography was specially normalized to HCP Connectome, HCP template space, so that we can have 2 different types of connectivity matrix, one with DCNN, another one is with DCNN. So from each of these 2 the matrix, we calculate the statistical significance of group difference in network topology at 4 different language areas, so including left inferior frontal operculus, insular and spherotemporal gyrus, and the angular gyrus. And also we calculate the significance of a functional correlate using CCA in those 4 areas. Okay, so this is the main event. So as marked by the yellow arrows, so conventional connectivity matrix includes such these the post-positive, which lowering our F values in group comparison. But using this DCNN, we could remove this outlier as shown in this example. Then we could improve the statistical significance as shown in this box. So bottom line, we could achieve 13 to 133% of F value just used by removing the post-positive fibers. So this one shows the exclusion of post-positive fiber. It does not depend on selected network type, topology type, or selected parameters is better. So as is shown in those plots, F value of different the network topology parameter, so looks pretty stable at different value of beta, which suggests that the exclusion of false positives using deep learning so provide to improve the statistical significance without depending on network type or the selected beta values.
Can you go a bit faster? You're
yeah,
going
so
over time.
this is the last one.
Right, yeah.
Okay, so this is showed how much we can improve the statistical inference in CCA analysis, where we used 4 different network efficiency of 4 language areas to predict actual language score in express receptive domain. So using the CNN, we could achieve this amount of the p-values. Okay, so bottom line, this work translate the advanced deep learning technique to improve the statistical inference in connectome analysis by efficiently removing false positive fiber from clinical DWI data. There is only one parameter we can control to exclude false positive outliers. Okay, better. So current implementation takes 10 minutes to classify 1 million fiber, but our data show that it helps a lot to generalize and standardize the pilot controls to ensure inter-subject reproducibilities in healthy control and epilepsy data. One drawback, it requires registration to whole body tractography to template space, which means that if you have some patient with severe cortical malformation, our implementation may not provide the high classification accuracy. So this is one. And also, most importantly, 3T human connectome project data is still suboptimal to exclude the false positive fiber, which means that our network already learned some pattern of false positives. So we're going to overcome these problems with a new data set in pediatric cohort and other patient cohorts. Thank you so much. Yeah.